Well, students, friends, this is a class on electromagnetic theory for 4th semester in physics for the academic year 2020-21. Well, friends, already I have uploaded the syllabus which I am going to teach for this semester. The electromagnetic theory and a part of optics, that is application part, say Michelson interferometer and its uses. Well, under this electromagnetic theory, which is prescribed for your syllabus of 8 hours, for your convenience as well as for my convenience, I have divided this topic into 3 parts. First part, it's a mathematical one, a mathematical background. What mathematical background we require here to study this electromagnetic theory? So mathematical background required for us is, say, field, scalar field, vector field, then gradient of a scalar, divergence of a vector, and curl of a vector field. Their physical meaning or physical significance. In addition to this, we need some theorems like Gauss theorem, Stokes theorem, and Green's theorem. We go for only the statement here as per the Karnataka University syllabus prescribed for your semester, that is 4th semester. This is first part. Mathematical background is the first part, and under this mathematical background we have like gradient of scalar, say divergence of vector field, and curl of vector, and some theorems, and say line integral, surface integral, and volume integral. This is the mathematical background we require to study electromagnetic theory. Well, now the second part of this topic, electromagnetic theory, is Maxwell's equation. So we want to derive this Maxwell's equations. There are 4 equations. In order to derive or understand this Maxwell's equations in its differential form, we need a mathematical background like Stokes theorem, Green's theorem, Gauss theorem, line integral, surface integral, volume integral, as well as gradient of a scalar, then divergence of a vector, and curl of vector. You might have studied this in vector algebra, in mathematics. Still, we require immediately to understand or to derive Maxwell's equation of electromagnetic theory. Once we derive the Maxwell's equation, maybe in its differential form and their integral form, while deriving this Maxwell's equation, mighty Maxwell's equation, I called here this Maxwell's equations are mighty Maxwell's equations of electromagnetic theory because nowadays everybody is using its application of Maxwell's equation. See, this Maxwell's equation, they are widely used in communication, any kind of communication, because we have a signal, maybe your mobile network signal or any other signal which is in the form of electromagnetic wave. And to understand this electromagnetic wave, we need electromagnetic theory, which is based on Maxwell's equations. But we obtained this Maxwell's equations in its differential form as well as in its integral form. Once we obtain this Maxwell's equation, there are four, based on Faraday's laws, based on Gauss laws, based on Ampere's circuital law. In fact, we know all these things like Faraday's laws of electromagnetic induction, Gauss laws of electrostatics or dielectrics in its differential form or in its integral form, and then Ampere's circuital law, its correction, say displacement vector, already we have studied it. All this we are using to know Maxwell's equations, either in its differential form or in its integral form. Once we understand this Maxwell's equations in its different forms, we are using them. But for what purpose we are using them? We obtain a general plane wave equation of a wave called as electromagnetic wave, and then we want to study its transverse nature. We know that light is having transverse nature, so electromagnetic wave is also having transverse nature, and we want to prove it mathematically. Other than this, we want to study how the energy is carried by this electromagnetic wave. The energy carried by the electromagnetic wave is known as Poynting vector or a Poynting theorem that we are going to study under this. Apart from this electromagnetic wave theory, I have to cover as a fourth part the application of electromagnetic theory, that is plane wave equation, transverse nature of electromagnetic wave, and say Poynting theorem, its derivation, happens to be third part of this electromagnetic theory. In addition to this, I want to cover a portion on interference. I may not begin this topic interference from the beginning. The senior person is doing that. The other one, the application part of this, that is Michelson interferometer, an instrument, its construction, its working, and where it is used. So to determine wavelength of a light, we are using this Michelson interferometer to find the circular fringes, to find the straight fringes, elliptical fringes, and we are making use of this Michelson interferometer to standardize a meter scale, a standard meter scale, how it is standardized using interference as an application using Michelson interferometer. This is, and the problems based on this. This is what I am going to discuss for this semester, whether it is online or offline. Well, we'll come to this electromagnetic theory. Well, so as I mentioned here, it requires mathematical background. Mathematical background. What mathematical background we need? I mentioned here the field, scalar field, vector field, how they are represented, and then how one field, say a scalar field, is converted into a vector field, or how a vector field is converted into a scalar. That is, finding gradient of a scalar, divergence of vector, and a curl of a vector field. These three topics we are studying as a mathematical background. In addition to this, we need a line integral, a surface integral, volume integral, and we are using these three integrals, line, surface and volume, to convert. So volume to line integral, line to surface integral, surface to volume integral. We are using three theorems: Gauss theorem, Stokes theorem and Green's theorem, without say the proof, and that comes under mathematical background. So the first part of electromagnetic theory, that is mathematical background, already I have uploaded the notes on this. Please go through the notes, and if you have any doubt, you do contact me. Let us start discussing what is called as a field. Fine. A word field, already you have studied this. This is not new for you. Well, we have electric field, we have magnetic field, we have different field, we have gravitational field, and so on. Electrostatic field, magnetic field. Well, in general, a field, let me consider here a space, a three-dimensional space. So this is x coordinate, y coordinate and z coordinate. This is Cartesian coordinate. If I consider any physical quantity, and if that in a space, and if that physical quantity varies from point to point in the space, then it can be expressed as a continuous function of position, say p of or phi of x, y, z. It can be expressed as a function of position, and it is known as position function. The region in the space in which the position function can specify a physical quantity is known as field. I'll repeat. Say the region in which a physical quantity or a region in which a position function specifies a physical quantity is called, say, a field. And we know, depending upon a physical quantity, I mean a scalar quantity or a vector quantity, we have two types of fields: a scalar field and vector field. Fine. A scalar field corresponding to scalar quantities. Scalar quantities, vector field corresponding to, say, vector quantities. Let me go for a scalar field and then we'll go for vector field. A scalar field, it's the region in a space. Maybe this is the region in a space, say in coordinates system, whose every point is characterized by the single value of a scalar quantity is known as a scalar field. I'll repeat. Say it's the region in which is the region in a space whose every point is characterized by a single value scalar quantity is called a scalar field. But this definition differs from author to author. It's not a unique definition like that. Different people, they define in a different way. We have defined the same thing, a scalar field, in PU second year, right, in a different way. So, what are the examples of this scalar field? Distribution of temperature or distribution of electric potential around a charged body. So, variation of electric potential around a charged body is an example of a scalar field. Variation of temperature from point to point along a metal rod, which is maintained at one end it's hot and the other end is cold. So the temperature varies. Distribution of temperature along a metal rod is an example of scalar field. We have, say, density distribution, non-directional density distribution is an example of, say, scalar field. Well, yes, we have defined a scalar field. Now, how to represent this scalar field? To represent this scalar field or a scalar function, say phi, is a scalar function, and this scalar function is variable of position r. I can represent this scalar function which varies with position from here, right? And this is r, the position vector. So this scalar functions are, say it is for x, y, z. Well, x, y, z are Cartesian coordinate. Then we denote this scalar function phi of r, where r is function of position, that is position variable. You can say phi of x, y, z is a scalar function. Now this scalar function or a scalar field is represented by drawing the level surfaces. We can draw, if this is a scalar field, imagine this is a scalar field. In this scalar field, we can draw the lines or we can draw the surfaces. For example, isothermal. We have used this term many a times in either in thermodynamics or in gas laws. A system is isothermal. The temperature is constant and it is represented in PV diagram. So by drawing, say, surface, and here this is equipotential surface, say equipotential surface. This surface is having equal potential. Potential is equally distributed. It's known as equipotential surface, and this concept also you have studied in electrostatics. Isothermal or equipotential surface. Equipotential surface. This scalar function is represented by equipotential surfaces like or isothermal. By drawing the surface, they are called as level surfaces. Level surfaces. Now, this surface is having constant value of its magnitude. Magnitude at a given point is constant, either at this point, either at this point, either at this or this. So magnitude is constant and therefore we call it as equipotential. Potential is uniform. Or isothermal, the temperature is uniform. This is in general. Say a scalar field is represented by drawing surfaces in a given field, and those surfaces are known as level surfaces, whose or at which the magnitude of the scalar function is constant. Say it is phi of x, y, z. If it is a scalar function, it is single value function. Single value function, or it is uniform at every point, either on this or at this surface. Its value is uniform at every point. So it is called as single value function. Say this value is constant. Phi of x, y, z is represented as scalar field. Let us go for a vector field. What is meant by vector field and how it is represented? Let me write here the vector field. This vector field, the vector field is represented at every point by a continuous vector function. Vector field is represented at every point in a space by a continuous vector function f of x, y, z is a vector function, and this vector function in a field is represented inside the field. Say that I am calling it as a vector field, and say this is its function at every point. The vector field is represented by this continuous vector function. At any given point in a field, say at any given point in a field, I will represent this as vector field. Say this is vector field. At any given point, this vector field is represented by its both magnitude and direction. If f of, say, x, y, z is a continuous vector function in a vector field, and at every point it is represented by both its magnitude and direction. Say this is, say, vector field. A point you can draw like this, f of x, y, z. F is a vector function, continuous vector function. So at this point represents both in magnitude and direction. This vector function has both magnitude and direction. So this magnitude and direction, it varies from point to point in a vector field, because the vector field is a continuous, represented by a continuous vector function. Well, this vector field is specified by both its magnitude and direction, and continuously its magnitude and direction changes from point to point. Now, how this vector field is represented? So this vector field is represented by vector lines. I may draw this as a vector line. Say I may call this as f is a vector, and it represents both by magnitude and direction. I may draw the vector lines. A curved line is a vector line, or called as curved vector line. Vector field is represented by vector lines, and right here, or curved vector lines. A common word we are using in our studies, that is vector flux lines. Vector field is represented by vector lines, curved vector lines, or vector flux lines. I want to represent magnetic field. Say here, these are the magnetic lines of force. We draw it. Magnetic lines of force. I want to represent electric field. So we draw the lines of force, electric lines of force. And we have studied lines of force, the characteristics, its importance in either in PUC first year or in second year. We studied it in under electrostatics, or the magnetic effect of electric current. Magnetic lines of force, electric lines of force, it is represented by, say, flux lines. So normally we call this as a flux lines. If I draw a flux line here, this is a flux line. Either it is a vector field in general, whether it is electric field or magnetic field, let us call it as, say, vector line, a curved vector line, or a flux line. Now, its magnitude and direction, how to find the direction and magnitude of a vector function is represented by vector lines, curved lines, or vector flux lines. From the flux lines or vector line, we can find out both magnitude and direction of a vector function, which is to be a continuous function. Well, if you draw a tangent at any given point, draw a tangent at any given point. Say I want to find the direction at this point, so I will draw the tangent, and the tangent tangent drawn at a particular point on a vector line represents the direction of a vector field at a given instant. Now, what about the magnitude? So, to find out the magnitude from the vector lines or flux lines, we draw a surface element, a small surface element, and the number of lines crossing this surface element per unit area perpendicular to the lines gives us the magnitude. Draw a surface, and how many number of lines, vector lines or flux lines crossing that element, surface element per unit area perpendicular to the direction gives us the magnitude. Well, this is a simple introduction to this mathematical background, what is called as field, vector field, scalar field, how vector field is represented, how a scalar field is represented. Vector field is here, it is represented by vector flux lines. Vector field can be mapped. You can use mapping can be done on the basis of flux lines. So vector field can be mapped on what is called as flux lines. What are the examples of vector field? There are many. Magnetic field is a vector field. Electric field is a vector field. Distribution of velocity of the gas is a vector field, and so on. So, in general, a vector field is represented by curved line or the flow of line or a flux line. Right. Let us go for the actual beginning of this syllabus, what is called as gradient of a scalar field. Gradient of a scalar field. Okay. To start with the gradient of a scalar field, we have to consider a scalar field, and